In this segment, we're going to talk about some improvements to the basic attentive reader model that we established before. So recall that that model looked like this. We had a bidirectional LSTM to encode the passage P. We had a unidirectional LSTM to encode the question Q into a vector. And then what we did was we took the single Q vector and all the P vectors, and we did an attention-like computation in two copies, one to produce a distribution over start positions for the answer, and one to produce a distribution over end positions for the answer. So I mentioned before that this model does not actually work very well, and there's a couple of improvements that we're going to make. And so these improvements are going to basically up the complexity of the model a bit and enable it to capture a little bit more detailed interaction between these two pieces in order to model the problem in a better way. So the first bit is what we call context to query attention. And so here's the basic idea. So we have these actually, let's see. What I'm going to do is I'm going to call the outputs of the P encoder. I'm going to call those xi now instead of pi, and you'll see why in a second. So we have x1, x2, x3, etc. And then we have the tokens in the question, which we are now going to encode, which we are now going to actually like look inside the question LSTM for. So we get these Q vectors like this. And the idea is that we want words in P to attend to Q. So what this is going to allow us to do is it's going to allow us to capture more detailed word-by-word interactions between the passage and the question. So right now you cook the whole passage down into one single vector, and then you compare it, or sorry, you cook the whole question down into one single vector, and you compare it to the passage. But what we want to capture in a lot of these cases are things like fine-grained entity matches. Like if you say, you know, what was the event that caused World War II or World War I or whatever, then you want to look for that specific occurrence of World War I or World War II, and you probably need that matching to happen at the word level, because once you kind of boil everything down into this very abstract vector, World War I and World War II are probably going to look pretty similar. So what we do is we do an attention computation where each xi attends to the question. So we're going to form a distribution that we're going to call alpha I, which is a softmax over j of xi dot qj. So again, the I is an index in P, and J is index in Q. And then we're going to form a vector that we call VI, which is the sum over J of alpha ij times Qj. So what this is doing is it's a weighted sum of question for this position in passage. So that is going to give us a vector up here. And then we're going to use that as part of the encoding for P. So we are then going to say, okay, this basically VI and XI concatenated together these are now going to be the PI vectors. So previously we were just using this bidirectional LSTM. I should have made this bidirectional here. We were just using this bidirectional LSTM output, which previously we were calling PI, now we're calling XI, but now we're adding on this additional term based on this attention computation. Okay, so that's change 1. Change 2 is we have a new way of encoding the question. So again, we're now thinking about the actual vectors internal to this question encoding process. And we can use a bi-LSTM here now as well. I set it up with a unidirectional LSTM before, but that's not, given that we're now kind of looking at the individual vectors and not trying to use it to produce some singular encoding, we might as well use a bidirectional LSTM. And if you use a bi-LSTM, you can, again, we mentioned this quite a while ago, but you can take the vectors from both sides and use those as a representation of the whole question anyway. So this, we have these vectors that come out of the bi-LSTM. And then what we are going to do is we are going to form the overall Q vector as the sum over, as a weighted sum over J, where each of these weights Bj So what we do is we have a fixed vector W of parameters. So this looks a little bit like an attention computation, but normally when we do attention, we have some notion of a query, where we're, for example, taking a hidden state of the decoder in machine translation and using that to attend to the input. Here instead we have a fixed vector. Well, it's a vector of parameters that will change during learning, but there's just one W vector that gets dotted with each question vector, Qj, so each position in the question. And that softmax produces a distribution over the question. And so what this allows us to do is it allows us to say, okay, this word in Q is important. And bi-LSTMs should be able to do this as well. It turns out this works a bit better. And so, we're going to have this, we're just going to sort of feed everything here into a, I'm just going to label this as number 2. And that's going to give us a new Q vector as output. So we made 2 changes. One is that the question is kind of influencing a lower level of the computation over the passage as well. And we are encoding the question in a new way. All right, so the ideas we've talked about here are presented in the DRQA paper by Chen et al. So I encourage you to look at that paper if you want to see a little bit more explanation of this. There's some additional details there as well, but this is really the kind of core stuff. And then there's another system that's very commonly used for QA called BiDAF by CO et al. And that system uses the context to query attention, and they also have a separate query to context attention, so they have a mechanism going in the other direction, and a couple of more tricks as well. They basically kind of staple in an extra LSTM on top, and there's a character CNN over the input. There's just generally a few more bells and whistles. And for a while, this was kind of accepted as one of the best neural net models for this task. And the big difference now is that we can do a lot of this stuff with BERT. And so the idea of designing these kind of custom architectures has a little bit fallen by the wayside. But what I will say is that this shows you some of the ideas that are very important to capture for question answering. In particular, we really need to get at this low-level interaction between words in the passage and words in the question. And we need enough parameters in this model and enough processing for the model to be able to learn this sophisticated mapping. So BERT is going to do that very easily through self-attention. But before BERT was around, this was the kind of architecture that people used, and it's still reasonably effective for these simple questions. The accuracies it can get are on the order of 60 to 70%, which isn't bad for a task that was basically totally impossible before neural nets came along, or the solutions were very brittle and did not achieve high accuracy on this data set. So this tells you a little bit about how to build better neural networks for reading comprehension, and that's the end of this segment.